Now, in this lecture, we find out the distance between the centers of two circles. In the drawing, we have rectangle ABCD. We know that side AB of this rectangle is equal to 7 units in its length, side BC equals to 24 units in its length. Inside this rectangle ABCD, we have those two circles. The center of this circle is here at point Q, the center of this circle is here at point P. And our mission is to find out the distance between the centers of those two circles, that is to say, the length of this line segment QP. Okay, and because of the fact that ABCD is a rectangle, it means that those four angles are all right angles, so I'll write it down. This angle equals to 90 degrees. This angle is also equal to 90 degrees. This angle equals to 90 degrees. And this angle also equals to 90 degrees. In addition, ABCD is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, side AB equals to side DC. But AB equals to 7 units in its length, therefore DC must be also equal to 7 units. Likewise, according to the sum rule, side AD must be equal to side BC, but BC equals to 24 units in its length, therefore AD must be also equal to 24 units in its length. So, angle ABC, this angle equals to 90 degrees, therefore triangle ABC is right triangle, so we will implement the Pythagoras theorem on this right triangle, triangle ABC. And according to the Pythagoras theorem, in the right triangle, triangle ABC, my PT is the progression for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So, the hypotenuse of the right triangle, ABC, is AC. Therefore, the square of the hypotenuse is AC squared. And it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to AB squared plus BC squared. Okay, again, in the right triangle, triangle ABC, according to the Pythagoras theorem, AC squared equals to AB squared plus BC squared. So AC squared equals to AB squared. AB is 7, therefore AB squared is 7 squared, that is 49, plus BC squared. BC is 24, therefore BC squared is 24 squared, that is 576. So we can find out that AC squared in total, it is equals to 49 plus 576, in total it is equals to 625. So AC squared equals to 625. We take a root out of this equation and we get that AC equals to the square root of 625, that's actually 25. So we found out that the length of the hypotenuse AC in the right triangle, triangle ABC, it is equals to 25 units. Here, AC equals to 25 units in its length. In the next step, we will develop a general formula for the radius of any circle that is blocked by a right triangle. So here we have triangle ABC is a right triangle. This angle equals to 90 degrees. This triangle ABC blocks this circle. We know that the radius of this circle is x. We will develop a formula for the radius of this circle. We develop this formula that we will find out the radius of this circle only by knowing the side lengths of this right triangle, triangle ABC, that blocks this triangle. Okay, so here point O is the center of the circle, point M, we define the point of tendency of tangent BC with this circle as M. So OM is the radius of this circle. The radius OM is drawn to point M, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius MO. That is to say, this angle equals to 90 degrees, and this angle equals to 90 degrees according to rule number 1. I'll pick it quickly on rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. Point O is the center of the circle. Point M is a point on the circle itself, therefore OM is the radius of this circle, that is equal to R. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. Whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle equals to 90 degrees according to this rule, rule number 1. So, repeat again, it's according to rule number 1. Tangent BC is perpendicular to the radius MO, that is to say this angle equals to 90 degrees and this angle equals to 90 degrees. We define the point of tendency of tangent AB with this circle as N. We join points O and N together by straight line. So ON is the radius of this circle, that is equal to x according to our definition. The radius ON is drawn to point N, that is the point of tendency of tangent AB with this circle, and whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. If AB is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle equals to 90 degrees according to rule number 1. So inside quadrilateral NOBM, we have 1, 2 right angles. The sum of right angles is 270 degrees. So, plus the fourth angle, in total they must be equal to 360 degrees. Therefore, the missing angle here, this angle must be equal to 90 degrees. In order to complete the sum of the angles in quadrilateral NOBM to 360 degrees, the missing angle here must be equal to 90 degrees. So inside quadrilateral NOBM, this quadrilateral we have 4 right angles. And therefore we will relate to quadrilateral NOBM as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, NO equals to BM. But NO is x, therefore BM must be also equal to x. Likewise, according to the sum rule, OM equals to NB. But OM is x, therefore NB must be also equal to x. So we can know that quadrilateral NOBM is not a rectangle but a square because of the fact that all of its sides are equal to each other, each side equals to x. What is the length of line segment AN? From the drawing, it is very easy to see. that AN equals to AB minus BN. Again, AB minus BN equals to AN. So AN equals to AB, that is A, minus BN, that is X. So in total, AN equals to A minus X. AN equals to A minus X. Likewise, what is the length of line segment MC? From the drawing it is very easy to see that MC equals to CB minus MB. Again, CB minus MB equals to MC. CB is B and MC is X. So in total, MC equals to B minus X. Okay, MC equals to B minus X. So here we have rule number 2. According to rule number 2, the lengths of two tangents from a common extreme point to a circle are equal. We have the common extreme point P. From the common extreme point P, we have two tangents to the circle, tangent PA and tangent PB. And according to this rule number 2, whenever you draw from a common extreme point two tangents to the circle, then the length of those two tangents must be equal to each other. In this case, PA equals to PB. So actually we can implement rule number 2 in our drawing. In our drawing, we have the common extreme point A. From the common extreme point A, we have two tangents to the circle, tangent AN, and the second tangent is this tangent. We define the point of tendency of tangent AC with this circle as point S. So from the common extreme point A, we have two tangents to the circle, tangent AN and tangent AS. And according to rule number 2, they must be equal to each other. That is to say, AN equals to AS. But AN equals to A minus X, therefore AS must be also equal to A minus X. Likewise, according to the same rule, rule number 2, if we focus on the common extreme point C, from the common extreme point C, we have two tangents to the circle, tangent CM and tangent CS. And according to rule number 2, they must be equal to each other. That is to say, CM equals to CS, but CM is B minus M, therefore CS must be also equal to B minus X. So the hypotenuse AC, it equals to 3 units in its length according to our definition from one side, but from the other side, AC equals to AS plus SC. Again, AC, the hypotenuse AC equals to AS plus SC. So I'll write it down. The length of the hypotenuse AC is C, and C equals to AS plus SC. So C equals to AS, that is A minus X, plus SC, that is B minus X. So C in total equals to A plus B minus X is minus 2X. So it is A plus B minus 2X. We add 2X to this equation and we get that C plus 2X equals to A plus B. We subtract 3 from this equation and we get that 2X equals to A plus B minus C. We divide this equation by 2 and finally we get that X, that is the radius of this circle, is equals to A plus B minus C over 2. So we succeeded to develop a formula for the radius of this circle, that is X, and we can now find out the radius of this circle, that is X, only by knowing the side length of this right triangle that blocks this circle. So X, the length of the hypotenuse OM, that is X, it is equal to A plus B minus C over 2. Okay, I'll repeat again. The length of this radius OM that is equal to X, it is equal to A, that is the length of side AB, plus B, that is the length of side BC, minus the length of the hypotenuse, that is C, over 2. Repeat again. X equals to A plus B minus C over 2. So we can use this formula in order to find out the radius of the circle that is blocked by the right triangle ABC. According to the new formula that we developed here, if we define the radius of this circle as R, then R, according to the new formula, R must be equal to AB plus BC minus the length of the hypotenuse, that is AC, over 2. Repeat again, the radius of this circle that is blocked by the right triangle ABC must be equal to AB plus BC minus AC over 2. AB is 7, minus BC is 24, minus the length of the hypotenuse AC, that is 25 over 2. So 7 plus 24 is 31, and 31 minus 25 is 6, and 6 over 2 is 3. So finally found out that the radius of this circle that is blocked by the right triangle ABC, it is equal to 3 units in its length. Likewise, we find out the radius of this circle that is blocked by the right triangle CDA. Okay. We define the radius of this circle as x. So the radius x of this circle must be equal to CD plus DA minus the hypotenuse CA over 2. Repeat again, the radius of this circle that is x, that is blocked by the right triangle CDA, must be equal, according to the new formula, to CD plus DA minus CA over 2. CD equals to 7 plus DA equals to 24 minus CA, that is 25 over 2. So finally we found out that the radius of this circle X that is blocked by the right triangle ADA equals to 7 plus 24 is 31, 31 minus 25 is 6, and 6 over 2 is 3. So X equals to 3. So both radii of those two circles, they are both equal to 3 units in their lengths. So here X equals to 3 units. We define the point of tendency of tangent BC with this circle as M. The radius PM is drawn to point M, that is the point of tendency of tangent BC with this circle, and whenever we have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius MP. If BC is perpendicular to the radius MP, it means that this angle equals to 90 degrees and this angle equals to 90 degrees according to rule number 1. Angle ABC equals to 90 degrees because ABCD is a rectangle. We define the point of tendency of tangent AB with this circle as point N. We join points P and N together by straight line. Pn is the radius of this circle that is equal to 3 units. The radius Pn is drawn to point N, that is the point of tendency of tangent AB with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NP. If AB is perpendicular to NP, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule number 1. So inside quadrangle NPBM we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So inside quadrilateral NPBM, we have four right angles, and therefore we can relate to quadrilateral NPBM as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, side NP must be equal to side BM, but NP equals to 3 units, therefore BM must be also equal to 3 units. Likewise, according to the sum rule, side PM of rectangle NPBM must be equal to side NB, but PM is 3, therefore NB must be also equal to 3 units in its length. So actually found out that quadrilateral NPBM is not a rectangle but a square because of the fact that all of its sides are equal to each other, each side equals to 3 units. If we repeat on the same process, on the other side, we get here that we will have another square here. If we define the point of tendency of tangent DC with this circle as the G, then QG is the radius of this circle that is equal to 3 units. The radius GD is going to point G, that is the point of tendency CD with this circle. And therefore, according to rule number 1, tangent DC will be perpendicular to the radius GD. That is to say, this angle equals to 90 degrees, and this angle equals to 90 degrees according to rule number 1. Point Q is the center of the circle. We define the point of tendency of tangent AD with this circle as E. QE is the radius of this circle that is drawn to point E, that is the point of tendency of tangent DA with this circle. Whenever we have a radius that is drawn to the point of tendency, then tangent DA will be perpendicular to the radius QE. That is to say, this angle equals to 90 degrees, and this angle equals to 90 degrees according to rule number 1. So inside quadrilateral EDQG, we have 1, 2, 3 angles, therefore the fourth angle must be also equal to 90 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And because of the fact that inside quadrilateral EDQG we have 4 right angles, we can relate to this quadrilateral EDQG as a rectangle, and know that the opposite sides of a rectangle are equal to each other. That is to say, QE equals to GD. But QE is 3, therefore GD must be also equal to 3 units. Likewise, according to the same rule, side QG of this rectangle must be equal to side AD. But QG equals to 3, therefore QE must be also equal to 3 units in its length. So actually found out that this quadrilateral QG ED is also a square because of the fact that all of its sides are equal to each other. Each side of this square is equal to 3 units. So in conclusion, we found out that those two quadrilaterals, they are both squares, and one side of those two squares is equal to 3 units in its length. Okay. In the next step, we will extend the radius EQ by a straight line until it touches side BC of rectangle ABCD. EQ as a radius, it is absolutely a straight line. When you extend a straight line by straight line, the result is a straight line. So here, the extended EQ will define the touching point of the extended radius EQ with this circle as point T. So here ET is one straight line because we extended the radius ET by a straight line. When you extend the straight line by a straight line, the result is a straight line. So ET is a straight line. Here we created quadrilateral CTDE. Inside this quadrilateral we have 1, 2, 3 angles. Therefore, the fourth angle must be also equal to 90 degrees. According to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees, the missing angle here must be equal to 90 degrees. So inside quadrilateral CTDE, we have 1, 2, 3, 4 right angles. Therefore, we can relate to this quadrilateral DECT is a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, DE equals to CT. But DE is 3, therefore CT must be also equal to 3 units in its length. In the next step, we'll extend the radius NP by a straight line until it just touches the side DC of rectangle ABCD. NP is a radius, it is absolutely a straight line, and when we extend the straight line by straight line, the result is a straight line. So we'll define the touching point of the extended NP with side DC as point S. So NS is a straight line. Inside the quadrilateral SCBN we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So inside quadrilateral SCBN, we have 4 right angles. Therefore, we can relate to quadrilateral SCBN as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, NB equals to SC. But NB is 3, therefore SC must be also equal to 3 units in its length. So we know that side DC in total it is equal to 7 units because the width of this rectangle ABCD is 7. So side DC minus DG minus SC. So DC, that is 7 units in total, minus DG minus SC must be equal to the missing side GS. Okay. So DC is 7 units, minus DG that is 3, minus SC that is also 3. So the missing side GS must be equal to 7 minus 3 minus 3, that is 1. So we found out that GS equals to 1 unit in its length. We have already found out that EDCT is a rectangle, but here ET is one straight line. If we focus on this side of the straight line ET at point Q, here the sum of the angles must be equal to 180 degrees. So which angles we have at this side of ET at point Q? We have this angle that is equal to 90 degrees plus the missing angle. In total they must be equal to 180 degrees. Therefore the missing angle must be equal to 90 degrees. According to rule number 2, that the sum of the angles on one side of a straight line is equal to 180 degrees. Likewise, DC is one side of rectangle ABCD, therefore it is absolutely a straight line. If we focus on this side of the straight line DC, at point G, the sum of the angles must be equal to 180 degrees. So which angles we have at this side of DC at point G? We have this angle that is equal to 90 degrees plus the missing angle. In total must be equal to 180 degrees according to rule number 2. Therefore the missing angle here must be equal to 90 degrees. Inside we define the intersection point here as point J. So inside quadrilateral JSCT we have 1, 2, 3 right angles, therefore the fourth angle must be equal to 90 degrees. I repeat again that ET is one straight line because we extended the radius EQ by straight line. The result is ET, that is also a straight line. So if you focus on this side of the straight line ET at point J, here the sum of the angles must be equal to 180 degrees. So which angles we have at this side of ET at point J? We have this angle that is equal to 90 degrees, plus the missing angle. In total, they must be equal to 180 degrees. Therefore, the missing angle must be also equal to 90 degrees. We focus on this side of the straight line DC at point S. At this side of DC at point S, the sum of the angles must be equal to 180 degrees according to the rule that I mentioned. So which angles we have at this side of DC at point S? We have this angle that is equal to 90 degrees plus the missing angle. In total, it must be equal to 180 degrees. Therefore, the missing angle here must be equal to 180 degrees according to the rule that I mentioned a couple of times, that the sum of the angles on one side of a straight line is equal to 180 degrees. So I actually found out that inside quadrilateral QGSJ, inside this quadrilateral, we have 1, 2, 3, 4 right angles. Therefore, we can relate to this quadrilateral QGSJ as a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, GS equals to QJ. Again, GS equals to QJ, but GS is 1, therefore QJ must be also equal to 1 unit. Likewise, QG must be equal to JS in rectangle QGSJ. QG must be equal to JS. But QG is 3, therefore JS must be also equal to 3 units in its length. Here we've already found out that quadrilateral NBCS is a rectangle, and we also know that the opposite sides of a rectangle are equal to each other. That is to say, BC equals to NS. Again, side BC of rectangle NBCS must be equal to the opposite side NS. But BC is 24, therefore NS must be also equal to 24 units in its length. I'll write it down that NS equals to 24 units. So NS minus NP minus JS, again NS that is 24 minus NP that is 3 minus JS that is 3 must be equal to the missing side PJ. Again, NS that is 24 minus NP that is 3 minus JS that is also 3 must be equal to the missing side PJ. Again, NS is 24 minus NP that is 3 minus JS that is also 3 must be equal to the missing side PJ. So in total, the missing side must be equal to 24 minus 3 is 24 minus 6, that is 18. So we found out that the missing side PJ equals to 18 units in its length. And we already found out that QJ equals to 1 unit in its length. If we focus on the upper side of the straight line NS at point J, here the sum of the angles must be equal to 180 degrees according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of NS at point J? We have this angle that is equal to 90 degrees plus the missing angle. In total, they must be equal to 180 degrees. Therefore, the missing angle here must be equal to 90 degrees. So if angle QJP equals to 90 degrees, it means that triangle QJP is a right triangle. This triangle QJP is a right triangle because of the fact that angle QJP equals to 90 degrees. So I copy the right triangle QJP in a new page and implement the Pythagoras theorem on this right triangle QJP. Okay. So actually, this is the right range triangle QJP that they copied from the original drawing. Side QJ equals to 1 unit in itself, side PJ equals to 18 units in itself. And we are looking for the length of the hypotenuse QP. That is the question that we want to answer on this lecture. So we implement the Pythagoras theorem on this right triangle QJP. According to the Pythagoras theorem, if by PT is the progression from Pythagoras theorem, the square of the hypotenuse is QP squared. It must be equal to QJ squared plus PJ squared. So QP squared, that is the square of the hypotenuse, equals to QJ squared. QJ is 1, therefore QJ squared is 1 squared, that is 1, plus PJ squared. PJ is 18, therefore PJ squared is 18 squared, that is 324. So QP squared, that is the square of the hypotenuse, equals to 1 plus 324, that is actually 325. We'll take a root out of this equation and we get that QP equals to the square root of 325. But 325 is 25 times 13. We can take 25 out of the root, because we know that the square root of 25 is 5. We do it now, we get that the square root of 25 is 5. Inside the root, we left only with 13. If we're going to find out that the length of the hypotenuse QP, that is actually the distance between the centers of those two circles, equals to either 5 times square root of 13 units, or in terms of numbers, it is equal to 18.03 units. A little bit more than 18 units. Repeat again. The answer to this question is the distance between the centers of those two circles, that is to say, the length of this line segment QP, equals to either 5 times square root of 13 units, or in terms of numbers, it is equal to 18.03 units. Okay, so in the next step, I'll summarize the lecture. So in this lecture, we found out the distance between the centers of those two circles. The center of the circle is here at point Q, and the center of the circle is here at point P. So we found out the length of this line segment QP. In the drawing, we have rectangle ABCD. The width of this rectangle is AB, is equal to 7 units, and the length of this rectangle ABCD is BC, that is equal to 24 units. So inside this rectangle ABCD, we have those two circles, and our mission is to find out the distance between the centers of those two circles. That is to say, that to find out the length of line segment QP. Because of the fact that ABCD is a rectangle, it means that all the 4 angles here are right angles. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, side AB equals to side DC. But side AB equals to 7 units. Therefore, side DC must be also equal to 7 units in its length. Likewise, according to the same rule, side BC of the rectangle ABCD must be equal to side AD. But BC is 24, therefore AD must be also equal to 24 units in its length. Then we focused on the right triangle, triangle ABC. We implemented on this right triangle, triangle ABC, the Pythagoras theorem. According to the Pythagoras theorem, in this right triangle ABC, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse of the right triangle ABC is AC, therefore the square of the hypotenuse is AC squared, and it must be equal to AB squared plus BC squared. So AC squared, that is the square of the hypotenuse, must be equal to AB squared. AB is 7, therefore AB squared is 7 squared, that is 49, plus BC squared. BC is 24, therefore BC squared is 24 squared, that is 576. So in total, the square of the hypotenuse AC squared equals to 49 plus 576 is 625. We took a root out of this equation and finally found out that AC equals to the square root of 625, that is 25. So the length of this hypotenuse AC of the right triangle ABC, it is equal to 25 units in its length. Then we developed here, this circle is blocked by the right triangle ABC, and this circle is also blocked by the right triangle ADC. So those two circles, they are both blocked by right triangles. So in the next step, we actually developed a general formula that will help us to find out the radius of any circle that is blocked by a right triangle. This is the right triangle ABC, this angle equals to 90 degrees, therefore triangle ABC is the right triangle. Inside this triangle ABC, we have this circle that is blocked by the right triangle. The center of this circle is here at point O, and the radius of this circle is x. Our mission is to find out a general formula for the radius of this circle that is x, that we can find out the radius of this circle that is x only by knowing the side lengths of this right triangle that blocks this circle. Okay? So point O is the center of the circle. Side BC of the right triangle is tangent to the circle at point M. We join points O and M together by straight line. OM is the radius of this circle that is equal to x. The radius OM is drawn to the point of tendency, therefore according to rule number 1, tangent BC will be perpendicular to the radius MO. That is to say, this angle equals to 90 degrees and this angle equals to 90 degrees. We define the point of tendency of tangent AB with this circle as n. We join points O and N together by straight line. ON is the radius of this circle that is equal to x. The radius ON is drawn to point N, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. If AB is perpendicular to NO, it means that this angle equals to 90 degrees and this angle equals to 90 degrees according to rule number 1. So inside quadrangle NOBM, we have 1, 2 third angles, therefore the fourth angle must be equal to 90 degrees. So inside quadrangle NOBM, we have 4 angles, therefore we can relate to this quadrangle NOBM as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other, that is to say NO equals to BM. But NO is x, therefore BM must be also equal to x. Likewise, according to the same rule, side OM of the rectangle NOBM must be equal to side NB. But OM is x, therefore NB must be also equal to x. We actually found out that quadrangle NOBM is not a rectangle but a square. Why? Because all of its sides are equal to each other, its side equals to x. Okay. What is the length of line segment AN? From the dome it is very easy to see that AN equals to AB minus NB. Again, AB minus NB, it is AN. So AN equals to AB, that is A, minus NB, that is X. So in total, AN equals to A minus X. Likewise, we found out the length of this line segment MC. From the dome it is very easy to see that MC equals to CB minus CM equals to CB minus MB. Again, CB minus MB equals to MC. So MC equals to CB that is B minus MB that is X. So in total, CM equals to B minus X. So in conclusion, you can say that MC equals to B minus X and AN equals to A minus X. Then I presented to you rule number 2. According to rule number 2, the lengths of two tangents from a common standpoint to a circle are equal. Here we have the common standpoint point P. From the common standpoint point P, we have two tangents to the circle, tangent PA and tangent PB. According to this rule number 2, the lengths of those two tangents must be equal to each other. That is to say, PA equals to PB. So we can actually implement rule number 2 in our drawing. Why? Because in our drawing, we have the common standpoint point A. From the common standpoint point A, we have two tangents to the circle, tangent AN and tangent AS. And according to rule number 2, they must be equal to each other. That is to say, AN equals to AS. But AN is A minus X, therefore AS must be also equal to A minus X. Likewise, if we focus on the common standpoint point C, from the common standpoint point C, we have two tangents to the circle, tangent CM and tangent CS. And according to rule number 2, they must be equal to each other. That is to say, CM equals to CS. But CM is B minus X, therefore CS must be also equal to B minus X. So we found out that from one side, the length of the hypotenuse AC is C units according to our definition. From the other side, AC, the hypotenuse AC equals to AS plus SC. Again, the hypotenuse AC in total equals to AS plus SC. So we can write here that C, the length of the hypotenuse C of the right triangle ABC equals to AS plus SC. So C equals to AS, that is A minus X, plus SC, that is B minus X. So in total, C equals to A minus X plus B minus X. We open the brackets here, we got that C equals to A plus B minus X minus X. Minus X minus X is minus 2X. So in total, this expression equals to C equals to A plus B minus 2X. Then we added 2X to this equation and found out that C plus 2X equals to A plus B. Then we subtracted C from this equation. And finally we got that 2x equals to A plus B minus C. Then we divided this equation by 2 and finally we found out that x equals to A plus B minus C over 2. Okay, so here we developed a general formula to find out the radius of a circle that is blocked by the right triangle ABC. And we can find out the radius of this circle only by knowing the side lengths of this right angle that blocks the circle. That is to say, the radius x must be equal to A, that is the length of side AB, plus B, that is the length of side BC, minus the length of the hypotenuse AC, that is C, over 2. Again, the radius of this circle x that is blocked by the right triangle ABC equals to A plus B minus C over 2. We can use the new formula in order to find out the length of this radius of this circle that is blocked by the right triangle ABC. According to the new formula, we get that the radius R of this circle that is blocked by this right triangle ABC, the radius R must be equal to AB plus BC minus AC over 2. Repeat again, the radius of this circle that is blocked by the right triangle ABC, it must be equal, according to the new formula, to AB plus BC minus AC over 2. AB is 7, BC is 24, and the hypotenuse AC is 25. 7 plus 24 is 31, 31 minus 25 is 6, and 6 over 2 is 3. So finally we found out that the radius of this circle R equals to 3 units. Likewise, we found out, according to the same formula, the radius of this circle that is blocked by the right triangle CDA. According to the new formula, the radius x of this circle must be equal to CD plus DA minus CA over 2. Repeat again, the radius of this circle x must be equal to CD plus DA minus CA over 2. CD is 7, DA is 24, minus CA, that is 25, this is the length of the hypotenuse, over 2. 7 plus 24 is 31, 31 minus 25 is 6, and 6 over 2 is 3. So I found out that the radius of this circle also equals to 3 units in its length. Then we implemented rule number 2 here. Point P is the center of the circle, point M is the point of the circle itself, therefore PM is the radius of this circle is equal to 3. The radius PM is drawn to the point of tendency, that is to say it is drawn to point M, that is the point of tendency of tangent BC with this circle. Whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius MP. That is to say this angle equals 90 degrees and this angle equals 90 degrees. This angle equals 90 degrees because ABCD is a rectangle. We join points P and N together by straight line. Pn is the radius of this circle that is drawn to point N, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NP. That is to say this angle equals to 90 degrees and this angle equals to 90 degrees according to rule number 1. So inside quadrilateral PN BM we have 1, 2, 3 angles, therefore the fourth angle must be equal to 90 degrees. And because of the fact that quadrilateral NPBM has 4 rectangles, we can relate to this quadrilateral NPBM as a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say NP equals to BM. But NP is 3, therefore BM must be also equal to 3. Likewise, according to the same rule, side PM equals to side NB. But PM is 3, therefore NB must be also equal to 3. So after we found out that quadrilateral NPMB is not a rectangle but a square. Why? Because all of its sides are equal to each other, each side equals to 3 units. We can repeat on the same process exactly in the other circle, and we will get that quadrilateral GQDE is a square and each side of this square also equals to 3 units. So we have here 2 squares. And in the next step, we extended the radius EQ by straight line until it touches side BC at point T. EQ is a radius that is absolutely a straight line. And when you extend the straight line by straight line, the result ET must be also a straight line. So ET is a straight line. Inside quadrilateral EDCT, we have 1, 2, 3 angles, therefore the fourth angle must be equal to 90 degrees. So inside quadrilateral EDCT we have 4 angles, therefore we can relate to this quadrilateral EDCT as a rectangle, and we also know that the opposite sides of the rectangle are equal to each other. That is to say ED equals to TC, but ED is 3, therefore TC must be also equal to 3. Okay, then we know that side DC equals to 7 units in itself. So in rectangle EDCT, side DC must be equal to side ET. But DC equals to 7 units, therefore ET must be also equal to 7 units. Okay, then from point, and we extended the radius NP by straight line until it touches the circle, until it touches side DC at point S. When we extend the straight line by straight line, the result is a straight line, so NS is a straight line. So inside quadrilateral NCBN we have 1, 2, 3 angles, therefore the fourth angle must be equal to 90 degrees, therefore quadrilateral NBCS is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say NB equals to SC, but NB is 3, therefore SC must be equal to 3 units. Okay, so here we know that DC in total equals to 7 units. So DC minus DG, that is 3, minus SC, that is 3, must be equal to the missing side, GS. So DC is 7, minus DG, that is 3, minus SC, that is 3, must be equal to the missing side, side GS. So the missing side GS must be equal to 7 minus 3 minus 3, that is 1. So we found out that GS equals to 1. And here, this angle equals to 90 degrees, therefore the missing angle must be also equal to 90 degrees, according to the rule that the sum of the angles on one side of the straight line is equal to 180 degrees. This angle equals to 90 degrees, therefore the missing angle must be also equal to 90 degrees, according to the same rule. Likewise, we know that inside quadrilateral JTCS we have 1, 2, 3 angles, therefore the fourth angle must be equal to 90 degrees. So at this side of the straight line ET at point S, this angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees. Likewise, in this side of the straight line, this point S, this angle equals to 90 degrees, therefore the missing angle must be also equal to 90 degrees. So inside quadrilateral QGSJ, we have 1, 2, 3, 4 right angles. Therefore, we can relate to this quadrilateral QGSJ as a left angle. You know that the opposite sides of a left angle are equal to each other. That is to say, QG equals to JS. But QG is 3, therefore JS must be also equal to 3. According to the same rule, GS must be equal to QJ in this left angle. But GS equals to 1, therefore QJ must be also equal to 1. Then we have already found out that NBCS is a rectangle, and you know that the opposite sides of a rectangle are equal to each other. That is to say, BC equals to NS. But BC is 24, therefore NS must be also equal to 24 units in its length. What is the length of PJ? PJ must be equal to NS, that is 24, minus NB, that is 3, minus JS, that is also 3. So in total, PJ equals to 24 minus 3 minus 3. That is actually 24 minus 6. 24 minus 6 is 18. So I found out that the missing side PJ, equals to 18 units in its length. So this angle equals to 90 degrees. If you focus on the upper side of the straight line NS at point J, here the sum of the angles must be equal to 180 degrees according to rule number 2. So which angles we have at the upper side of NS at point J? We have this angle that is equal to 90 degrees plus the missing angle. In total they must be equal to 180 degrees. Therefore the missing angle here must be equal to 90 degrees. Therefore the right green triangle QJP is the green triangle QJP is a right triangle because this angle equals to 90 degrees. So I copied the right green triangle QJP in a new page and implemented the Pythagoras theorem of this green right triangle QJP. This is the right triangle QJP that I copied from the original drawing. According to the Pythagoras theorem, QP square equals to QJ square plus PJ square. So QP square, that is the square of the hypotenuse, equals to QJ square. QJ is 1, therefore QJ square is 1 square, that is 1, plus PJ square. PJ is 18, therefore PJ square is 18 square, that is 324. So in total QP square equals to 324 plus 1, that is 325. Then we took a root out of this equation and found out that QP equals to the square root of 325. But 325 is 25 times 13. We can take 25 out of the root and we get that the square root of 25 is 5. So in total this expression equals to 5. And inside the root we left only with 13. So found out that the distance between the centers of those two circles, that is to say the length of this isoelement QP, it is equal to either 5 times square root of 13 units, or in terms of numbers, QP equals to 18.03 units. Okay, thank you very much.